Okay. This will be a talk, a brief summary about what we have done in the past year and what we are going to do in the coming year for the libOMM. This is John Wall with Jianfeng Lu. I will discuss two main directions for libOMM at this current stage, and discuss some future direction for libOMM for finite temperature in this talk. So the first part of this talk is about some mathematics for OMM, and the second part will be some detailed implementation for libOMM, especially for the matrix multiplication. And finally, the last part is for future direction. We try to use optimization to identify the low-lying eigensubspace for given Hamiltonian matrix H. So the standard optimization problem is to minimize the variable quotient with the orthonormal constraint. From the high-performance computing perspective, this might be expensive because of the orthonormal constraint. So this motivates us to study another optimization problem, which is called the orbital minimization method, OMM for short. So in this optimization problem, the orthonormal constraint has been absorbed in the objective function. So we don't. It's an unconstrained optimization problem. We don't need to orthonormalize the object X in the iteration. So it might be cheap in this sense. The OMM method was proposed maybe more than 20 years ago, and we refixed this problem recently. A nice thing for this problem is that we can prove that all the local minima of the OMM are also global minimums. So we can start from any initial guess and just try to get a local minimum. Then that's it, we can get a global minimum. So as you can see, because we don't have the orthonormal constraint, so only matrix complication.
Quick question, maybe for John. I think that I don't understand. So there can only be one global minimum, right? Or can there be?
They have the same energy.
So it could be many local minimum, but they're all at the same energy.
Aha. And this is still true. There are systems that have different stable SCF solutions, right?
This is only the linear part. So it's a given Hamiltonian matrix, but it's not enough.
Okay.
So all the eigenvalues map to some constant energy.
Well, you need total energy. Yeah, sum over it.
Oh, the trick.
Yes. Sorry.
Could you repeat that more loudly, please? Because I didn't get the reply.
Which one?
The reply to why there can be several local minima.
They're all at the same energy was the answer, I think. And then I said, but there are different SCF stable solutions. But I think pointed out that this here isn't the nonlinear problem, of course. It's the linear eigenvalue problem where Hamiltonian and overlap are fixed.
Okay.
For that problem, there's only one set of global minima that all have the same energy.
Okay. Thank you.
Okay, let's move on. So as you can see from the optimization problem, it only involves matrix multiplication and addition. So it might be efficient and it might be a good alternative to direct diagonalization. In the case, for example, if we have sparse Hamiltonian or Hamiltonian with plane wave discretization, so that we can apply Hamiltonian efficiently. And also in the case if we have some good initial guess, for example, in the SCF iteration, in the later steps, we might have good initial guess for the optimization problem. And if we use that initial guess, then probably we only need a few iterations to converge. So the above are some brief summary about the OMM model. Next, I'm going to talk about the first direction about the libOMM, some direction about mathematics. So in this direction, we have explored various optimization methods to solve the OMM problem. And if the OMM problem has very large condition number, we try to design efficient preconditioner to reduce the condition number so that we can converge in very few iterations. We have explored many optimization methods to solve this problem, and the best method seemed to be the BiBi bovine method, which is BiBi for short. So I will summarize some key idea of some optimization, some method to solve the BiBi method to motivate the purpose of the BiBi algorithm. So let me use f of x as the energy that we try to minimize. So a very simple idea to minimize this energy is to use the gradient method, but the gradient method might converge slowly if we have very large condition number. So this also motivates us to think about Newton's method. But if we use Newton's method, then we have to compute the Haizhao, which might be very large, and we also need to invert Haizhao, which is very expensive. So this motivates the purpose of the BiBi method. In the BiBi method, instead of computing the Haizhao matrix F, we use some least square to get a diagonal matrix, which is alpha k times identity, to approximate the Haizhao in the sense of that we have the equation at the bottom instead of using the exact equation for the Haizhao matrix. So we can think about BiBi method as the gradient method with the step size computing from the least square to have some effect like applying the Haizhao matrix. So the BiBi method is very simple and it's very efficient. I will compare the BiBi method with the conjugate gradient method to see its performance. In this toy example, I use some Gaussian well to get some potential energy as V and design some Hamiltonian using the formula here. So I just randomly remove some Gaussian well from a periodic Gaussian well potential, and then design the Hamiltonian using this potential energy operator, and compare the BiBi algorithm with the CG algorithm. Here we have two kinds of BiBi algorithm with different safeguard. As you have seen, the BiBi algorithm is quite aggressive. Instead of using the Haizhao, we use the diagonal matrix to replace the Haizhao. So we cannot guarantee that the energy will decrease after each step of the BiBi algorithm. So we have to use some safeguard to guarantee the convergence of our algorithm. Depending on the different safeguard strategies, we will have different BiBi algorithm. Here we have tried two kind of safeguard. The first kind of safeguard is for ABB for short. So we compute the gradient and then we use BiBi algorithm to get the step size. If the step size cannot reduce the energy, then we will do some line search along this gradient to make sure that we will have some decrease in the energy. That's the main idea of ABB. For the BBSD, the main idea is that we perform a few steps of BiBi iteration, and then we will perform one step of steep descent to guarantee and then look back to the result before this few step of BiBi and compare these two kind of results. If BiBi can create energy, then we accept the result of BiBi. Otherwise, we will choose the result of SD, steep descent, so that we can have some safeguard to guarantee the decrease of the energy. So this is the BBSD. I will compare these two kinds of BiBi algorithm with the CG algorithm. In the case of preconditioner, I think PCG is a very powerful method for minimizing the energy. So for the Hamiltonian with plane wave discretization, usually we have the standard preconditioner for this kind of problem, which is called TPA preconditioner in electron structural calculation. So if we use plane wave, then we have powerful preconditioner. So I'm going to compare the precondition BiBi algorithm with the precondition CG. As you can see in this numerical example, So if you look at R time, which is the ratio of runtime of CG over BBSD, and the ratio of runtime of ABB over the time of BBSD. So the result of BBSD is always 1, and the result for CG is the speed up factor of BBSD over CG, and the result for ABB is the speed up factor, probably not speed up factor, because sometimes it's smaller than 1. So as you can see, in these results, the BB algorithms are always better than the PCG algorithm for the plane wave discretization, where we have good preconditioner. And in the case if we don't have a good preconditioner, for example, if we have some sparse Hamiltonian and we might not have good knowledge to get a good preconditioner, then the BB algorithm is much better than the CG algorithm. So
this n is the size of matrix or the number of eigenvalues?
The size of matrix.
How many eigenvalues?
How many eigenvalues? It depends on the Gaussian value we have. Usually, for each Gaussian value, I use A by A grid points. So you divide it by 64, and over 64 will be the number of eigenvalue we want to compute. Any more questions?
Can we go back to the curves? What is
Next one. Okay. So this is the first part of the math about libOMM. In the second part, I will discuss some preconditioner for OMM. So the OMM in the OMM optimization problem, we can intuitively prove that the condition number of this problem depends on the gap of the gap around the Fermi energy and the width of the spectrum of the Hamiltonian matrix H. So if the gap is very small, say if lambda n plus 1 minus lambda n is very small, here n is the number of eigenvalue what we want to compute, and then the condition number could be very large. And if the spectrum width is very large, say lambda capital N minus lambda 1 is large, then the condition number is also very large. So minimizing this problem might take many steps. Question is whether we can design some good preconditioner to reduce reduce the condition number, to reduce the number of iterations. So in DFT community, a very standard precondition might be the shifted Laplacian. And for plane wave discretization, a standard precondition might be the TPA preconditioner. They have some common intuitively. For example, for the shifted Laplacian, it enhances some part of the spectrum and then the other part of the spectrum in the frequency domain. And for the TPA precondition, essentially it behaves like a low pass filter. So it enhances the low frequency part and then the high frequency part. So essentially, for these two kinds of preconditioner, it's like it has some effect like drawing a Gaussian function. The Gaussian function will enhance the part for the Gaussian part, and for the tail part it will damn the effect. So this motivates us to think about some preconditioner based on this intuition. So the intuition is that if we want to compute some eigenpairs or some eigen subspace, can we design some preconditioner that can enhance the part corresponding to the target subspace and then the other subspace? So a very good possible solution might be the spectral projector. If we know the spectral projector exactly, then it's easy to compute the eigen subspace. but the question is how to compute that the spectral projector. That's the that's the main point for OMM. We minimize energy to get the spectral the eigen subspace, which is equivalent to the spectral projector. Now the idea is that we probably can compute the approximate spectral projector, and we can use this approximate spectral projector as the preconditioner for the OMM minimization problem. Now, a very simple idea for the spectral projector might be using some polynomial that can enhance the part corresponding to the target subspace, target eigenvalues, and then the other part we don't want. So Chebyshev polynomial might be a very good choice because it has some uniform. The error, the approximation error, is optimal in terms of uniform L infinity norm. The other, but if we want to use Chebyshev polynomial to approximate the spectral projector, then we might have some numerical issue like the Gibbs phenomenon. So some people propose to use some smoothing kernel to smooth out the Chebyshev polynomial to get a smoother result. But in general, the Chebyshev polynomial need very large degree to get a very good approximation to get a very accurate spectral projector. So this motivates some people to study the rational function, which is some polynomial over another polynomial. If we use rational function to get spectral projector, then we can get better result than the Chebyshev polynomial. But in the case of rational function, we have to solve equation. So if we have some Hamiltonian that can we can afford solving some multi-ship linear system corresponding to the given Hamiltonian, then we can use the rational function to get a very good approximate spectral projector as the preconditioner for the OMM minimization. In the plane wave discretization case, we can use some algorithm which is called the sparse-phi preconditioner to get good linear solver for the multi-ship linear system for the Hamiltonians, given Hamiltonian, so that we can get a good preconditioner for the OMM. So here is some numerical example. Again, we will use the same numerical example to show the efficiency of the proposed preconditioner based on the rational function. So for the rational function, one of the possible way to construct the rational function is to discretize contour integral in DFT. So in this example, I used 30 grid points to discretize the contour integral to construct the preconditioner. So we have to solve 30 equations to construct this preconditioner. But in hyperperformance computing, we can solve all these linear systems parallel. So this is not a big issue as long as we have many cores. And we don't want to solve the equations exactly, because if we solve the equation exactly, then we have to wait a long time. And for the second reason is that we don't need to get the precise spectral projector. We just need a rough spectral projector as the preconditioner. So we will use some iterative solver to solve these linear systems roughly, so that we can get something converged within a few steps. So here's the numerical results for the precondition OMM against some typical preconditioner for OMM. So the result SPP, the result of SPP is the result for the proposed preconditioner, and the result for TPA and GTPA are some existing preconditioner for OMM. So our new proposed preconditioner can speed up the runtime significantly from 10 to up to 70 or 80 times, and the speed up factor may increase if we have larger and larger problems. Here here is the problem size. And if you compare the error, then we can see that the new preconditioner can let the OMM to get a very good result. Even but the existing preconditioner cannot guarantee that the OMM can get very accurate result. So this is the part for preconditioning the OMM. So
what does it mean that OMM cannot be accurate? So you keep iterating.
Oh, I said I fixed the iteration number to 4,000. Of course, you can keep iterate, but it takes a long time.
So what is the, maybe I missed it, but what is the overhead for this preconditioner?
What is the
overhead?
Overhead.
Yeah.
So we need to solve the equation multi-strip linear systems.
But how much does this? So if you look at the block T tot, for instance, here, do you know what the overhead is compared to this log here?
The overhead, we use the specified preconditioner as a preconditioner to solve the multi-strip linear system. Mm-hmm. So for this iterative solver for linear system, it only takes about less than 75 iterations to solve. But the overhead for constructing the specifying preconditioner for the multi-strip linear system is to factorize a sparse matrix, just like selective factorization.
But so if you compare it quantitatively to these timings here?
It's some pre-computation. So we didn't put the time for constructing the specified preconditioner into the result here.
How it compares relative to? Is it like a 10%?
That we don't have result to compare that. So at this moment I cannot answer your question, but later I can check the computation.
What's the largest matrix size? Log n is 12. Is that 2 to the 12 or?
Which one?
So the size of the matrix, the
size of matrix,
log n.
Log n.
Yeah,
I don't remember. It's 2 to the n or 10. Oh, it should be 10 to the n. It should be
10 to the 12.
Or 2 to the n. 2 to the n. Yeah. Log 2.
Or e.
Log e.
Log e. I guess log.
What did you put?
I guess it's log 2 when I draw the figure.
Log 2.
That's fine.
log in MATLAB is log.
Log e.
Log is I think it's a log.
Anyway.
Okay. Yeah.
Okay. Any more question?
Okay. So basically, the matrix size is about 1,000 or 2,000, something like that.
I guess the matrix size is the same like the results here.
4,000.
We just repeat the examples again, using different method to solve the OMM.
Then must be e to the whatever. Because the 2 to the 12 is 4,000.
Okay. Okay. So I guess I just use log of n in MATLAB. So in the second part, it's for the some detailed implementation of libOMM. So if
probably just speed up.
Okay. Oh, so if we look back to the OMM algorithm, so we just need matrix multiplication. So this motivates us to design some efficient algorithm to perform the matrix multiplication. Especially when we have sparse matrix, we want to have efficient algorithm for computing this sparse matrix multiplication or sparse matrix dense matrix multiplication. If we don't want to do linear scaling, so this motivates us to develop the parallel and sparse bus, which is PSP for short. It's still under development, but it has. We have some routine already for the OMM. For example, we have 1D and 2D block circuit distribution to distribute the matrix, and we have sparse matrix formats, say COO and CSC available to compute the sparse dense matrix multiplication and sparse matrix multiplication. Here are some results comparing the matrix multiplication in PSP and scale APEC. As we can see, if we have sparse matrix, then we can get significant speed up over the dense matrix multiplication. You might have a question why we only have the dense times sparse matrix, which is significantly more efficient than the other routines in PSP. So this is due to the cache level optimization. I will have some results here to show the explanation. So this is the comparison between the sequential sparse bars in PSP and MKL. So in MKL, the only available routine for sparse bars is sparse matrix times a dense matrix. So I compare the sparse matrix times dense matrix in PSP and also MKL. So as you can see in this figure, the PSP implementation is less efficient than the MKL implementation. But if we, the sparse times dense can also be considered as dense times sparse and then compute the transpose of the result. So if we look at the routine of PSP for the dense matrix times sparse matrix and then compute the transpose, then we realize that PSP, the PSP with MSPM dense times sparse is more efficient than the sparse times dense in MKL. So I checked the code and realized that that's due to the cache level optimization of the coding. So for the PSP is coded in Fortran and using CSC format, so it's more efficient to compute dense matrix times sparse matrix than sparse matrix times dense matrix. So if we use C purpose to make a sparse bars to compute sparse matrix times dense matrix, I believe we can get better results than MKL. At least at this moment, a very simple trick is to use dense times sparse and then compute transpose to replace sparse times dense in MKL. So that's the second part of libOMM. So in the last part is about some future implementation for OMM for finite temperature system. For finite temperature systems, we are not only interested in the low-lying eigensubspace, we also need to compute the eigenpairs near the Fermi energy. So in this case, we propose to use OMM to identify the low-lying eigensubspace and use some interior eigensolver to identify the interior eigenpairs. A possible choice is to use some routine from spectral slicing idea. So we can construct a very precise rectangular approximation to approximate the rectangular function so that we can get a spectral projector. We have two ways to construct the approximation, as you have seen, the Chebyshev polynomial and the rational function. Recently, we have proposed the optimal approximation to the rectangular function using the rational function for fixed orders. And we have also developed some fast and stable algorithm to evaluate this, to apply this spectral projector with high orders. So that's all of my presentation. Any question?
So this OMM project, I think you told me, but I can't remember. So is there any way to do like deflation? Eigenvalue, if they don't converge at the same rate, right? So some of them will converge first, and then some others will converge more slowly. And typically, most eigensolvers you try to deflate because they converge.
Yeah, we have discussed a little bit 1 year ago, and I remember that we don't observe any convergence rate difference in OMM.
Okay. So you mean everything converges at the same time, basically, or you get the subspace? Yeah, you
can also think about this. We don't have any distinct. We don't distinguish the eigenvectors.
I know you don't. The algorithm itself doesn't distinguish that, but the subspace that you compute.
Maybe your idea might be we can divide the domain we are interested into several parts, and we want to compute the eigen subspace corresponding to these several parts, and maybe the low-lying parts might converge faster than the part near the Fermi energy.
Right, but in order to do that, you have to do some kind of Rayleigh-Ritz.
Yes.
Which you don't do right
which
now,
we don't
right?
do.
Yeah.
Which we plan to avoid,
Yeah.
which is one of the motivation of the OMM. So maybe we can explore to modify the OMM minimization.
Yeah, I'm just curious. I mean, because I don't have much experience with it. But I know we try to do something called penalized trace minimization. Deflation turns out to be very important there. But so we do Rayleigh-Ritz every once in a while.
Yeah.
This may be a very silly question, but go back one slide. Go back another slide, sorry. So you're saying that in the fully occupied eigen subspace, you would just do libOMM?
Yes.
How do you know what the fully occupied space is? Like you need to know the number of occupied states used libOMM, right? How do you estimate that from the beginning?
Yes. Usually the first iteration use alpha.
Okay. Okay.
I think at this moment, the state-of-the-art algorithm is also doing this, right? First few iterations using alpha, and the last few iterations using
True, that's what we're already doing in LD by default.
And your preconditioner from before, speaking of alpha, can't you also derive that in some way by solving the problem using an eigensolver first and then getting a very good approximation?
Yes. If we have good knowledge, well, if we have some approximate knowledge about the eigenpairs and eigenvalues, we can use them as preconditioner. For example, in this case, if we know if we have known the eigenpairs here, then we can use them to construct efficient preconditioner for OMM part, because the OMM, the condition number of the OMM depends on the width of the spectrum and also the gap. So if we use them to remove the eigenvalue corresponding to this part, then the gap will be very large. Then we might only need few iterations to converge for the OMM part.
Any other questions?
Anybody from outside this room by any chance?
Everyone there's so quiet.
Yes, it's very quiet.
This is Changmin. So I just have one question. So have you guys considered using lower precision during this iteration method? So I see that the number of iterations can be quite high, and especially when you start from the sort of almost random guess, then one possibility is just to walk around with a lower precision and then quickly go to the solution and then refine it. Is there something that can be explored and sort of evaluated easily?
I think Victor has explored this when he combined alpha and libOMM. Right.
Single precision? You mean?
I think she's,
Mixed precision. So let's say all the operations can be done in a mixed precision. Lower precision, possibly the inversion is the exemption, but I think
the alpha project is exploring something like this, I think, but not.
we've not done anything like mixed precision in LZ. We're always double.
Yeah, but for GPU, that would of course be also an interesting thing. That's true. So, and in alpha, something like this exists, I think, but in the current Munich alpha project, Christoph, I think, has just left, right? Yeah.
I think Christoph is on. Anyway. Okay. And with that, let's thank the speaker again.
Question though.